knows a lot about the science stuff. Professor Dave explains.
One of the more interesting industrial processes ever invented, the synthesis of petroleum from coal, was developed, like most other chemical processes of the early 20th century, by German chemists. Franz, Fischer, and Hans Tropsch, working at the Kaiser Wilhelm Institute for Coal Research in Mülheim an der Ruhr, were tasked with converting charcoal, which was abundant in Germany, into petroleum, the critical fuel for transportation at the time, something Germany did not produce in sufficient amounts to sustain their needs. Their breakthrough was announced in 1926 and was rapidly applied all over the world on an industrial scale. It became especially important to the Nazi regime, which needed large amounts of fuel in order to sustain war preparations. The process consists of the catalytic conversion of syngas, a mixture of carbon monoxide and hydrogen, into hydrocarbons, which act as fuel for modern gasoline engines. Syngas was obtained, at that time, primarily through the gasification of charcoal using steam at high temperature. That is shown here, where coal, which is elemental carbon, reacts with water to produce carbon monoxide and hydrogen gas, or syngas. Then, in a second reaction, carbon monoxide reacts with hydrogen gas in the presence of a catalyst at high temperature and pressure to produce hydrocarbons of varying length and water. This is the Fischer-Tropsch process. The catalysts consist of fine metal particles immobilized on an inert matrix, usually silica or alumina. The metal itself is usually iron or cobalt. Ruthenium also works, but it is more expensive, whereas nickel has much lower chain growth reactivity. Each metal has its own advantages and drawbacks, with formation of many possible unwanted products, such as methane, which offers no chain growth, olefins, alcohols, and ketones, which are less energetic, and aromatics. Catalyst optimization is still an active area of research. The temperatures can reach 350 degrees Celsius, and the pressure can be up to several bars. The hydrogen to carbon monoxide ratio is very important for an optimum yield of hydrocarbon. It is usually adjusted to the desired level, around 2:1, by increasing the temperature until the water-gas shift reaction becomes significant. This reduces the level of CO and increases the level of H2. Unfortunately, carbon dioxide is also produced in the reaction. Now let's discuss the mechanism. It is fairly well understood how hydrogen is activated by metals, and we have already covered this in an earlier hydrogenation tutorial. Essentially, the HH bond is broken at the metal surface, and metal hydride moieties are created, with the hydride being able to diffuse quickly across the surface. Carbon monoxide is activated to generate oxocarbide complexes, which are in equilibrium with a bridge mode-bound CO molecule. Both species may contribute to catalysis. From these oxocarbide complexes, two hydrides could add to form a hydroxyalkyl complex, which is further reduced to a methylene group by two further hydrides, releasing water. Next, several vicinal methylene groups are joined to form C-C bonds, followed by reduction and release of the hydrocarbon, in this case butane. In the case of the bridged CO, the initial species is split, resulting in M-carbide complexes and metal oxo complexes. These are both hydrogenated by bound hydrides, the oxo complex to water, which is desorbed, and the carbide to methylene, which can polymerize as in the previous example. The product distribution in the Fischer-Tropsch process is complex, since many different hydrocarbons can be produced. As we mentioned, an undesired product is methane by double hydride addition to an M-methylene residue, because it is not liquid. Efforts to avoid this have produced long-chain paraffins, which are waxy solids and are therefore also undesirable in liquid fuels. Usually, parameters are adjusted so as to avoid waxes, targeting hydrocarbons of 10 carbons or less, meaning that N-decane is usually the longest linear alkane that is acceptable. An interesting approach to syngas is the thermal gasification of biomass. Under appropriate conditions, biomass, primarily a mixture of cellulose, hemicellulose, and lignin, can be transformed into syngas, and this can be fed into a suitable Fischer-Tropsch reactor, producing bio-renewable gasoline. Given that petroleum will account for over 80% of our energy needs until 2040, the Fischer-Tropsch process may help us significantly to navigate the next few decades before our energy sources switch to carbon neutral. There are already many production plants in the world using the chemistry we just described. The largest is in South Africa, managed by the company Sasol, which produces 165,000 barrels of gasoline per day using the Fischer-Tropsch process. This is, of course, not particularly significant in terms of global oil consumption, as it represents only 0.17% of the daily world supply. Nevertheless, the technology has proven itself highly cost-effective and practical. This chemistry is still the subject of optimization research, as new production plants are brought online constantly throughout the world. Finally, it is widely believed that this process is relevant to the origin of life. It has been suggested that long-chain aliphatic molecules, like for example fatty acids, may have originated by naturally occurring hot metal surfaces acting as natural sources of syngas, followed by some oxidative process. Thus, nature may have devised this chemistry long before Fischer and Tropsch thought of the idea, and may have used it to enable the appearance of life on Earth.
Thanks for watching. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.